Hi, I'm Joel Kira from Georgia Tech. I'd like to thank the organizers for inviting me to give this talk. Today I'm going to be talking about learning with limited labels and robust multimodal fusion. And I'll talk about connections to agricultural domain throughout. So the rise of artificial intelligence has largely been driven by machine learning and deep learning in particular. And so there's been a large focus on kind of analyzing a whole wide range of kind of modalities of data, text, images, videos, audio, and so on. And so there's been a lot of tremendous progress made in these kinds of areas. Despite the kind of success, though, there's still a number of key challenges that exist in deploying these kinds of methods to, for example, effective solutions in agriculture. So I'll be talking about two of those in particular in this talk. The first one is that the current methods are still dominated by supervised learning, where you have very large kind of labeled data sets. So you can, if you're given a large labeled data set, you can optimize for a particular task and do really well. However, there's the amount gathering that much data is very difficult or cumbersome, especially if you want to do, for example, new regions across the country or the world for agriculture. And more importantly, the current methods don't really handle outer distribution data very well. So if you see something that you don't have in the training during testing, then kind of the neural network tends to output optimistically wrong answers. And so I'll be talking about kind of methods on how to address that. The second kind of issue that I'll be talking about is how to address the multimodal fusion. So given, for example, agricultural domains, you might have a large range of different sensors. So if you gather it from a UAV, it could be RGB, depth, structure for motion information, things like that. Or it could be multispectral or infrared, or there's a whole host of modalities that might be interesting. And so we still don't know kind of what the best method is for combining these, especially when there's various degradations in the environment, such as weather conditions or other things that might affect each sensor kind of differentially. So I'll talk about some methods that we've developed to do that. So in terms of reducing the amount of labeled data, there's been a lot of progress in the past 2 years. So the progress has been in a lot of different kind of machine learning formulations that range from sort of what's called few-shot learning or zero-shot learning, which is learning from a small amount of data. So a few examples, for example, for something completely new. There's been semi-supervised learning, self-supervised learning, which deals with a combination of labeled and unlabeled data sets or just unlabeled data sets, which obviously is much easier to gather. And then domain adaptation, for example, where you want to gather a training set from one region, let's say, of the country or the world, and then test it on another, and you want to sort of adapt the classifiers that are learned to these new regions. So my group has actually made contributions in a lot of these areas. So we started with sort of pairwise similarity for cross-task object discovery. So this is where you have a labeled data set, let's say from one set of object categories, but then you want to apply it on completely unlabeled data that has a completely different things. So this is kind of a clustering problem, and we developed one of the first deep learning based solutions for clustering, so loss functions for this. And then we've also looked at outer distribution detection. So how do you actually detect if things that are different from the training, and so that the classifier can say that it doesn't know. We've done few-shot learning with Virginia Tech, looking at kind of if you have only a few examples, 5 to 10 per category that's new, how can you do pretty well. And then we have methods that I'll be talking actually about in this talk on complex data augmentation for things like self-supervised learning or semi-supervised learning. So where you have a combination of labeled and unlabeled data. So in terms of these methods that leverage unlabeled data, data augmentation is one of the key kind of techniques that's used. So data augmentation is where you take a piece of either labeled or unlabeled data and you transform it in some way that preserves its semantic meaning. So you can add noise, for example, you could flip the image, crop it, and so on. And as long as what's in the image is still the same, you can kind of enlarge your data set by performing these data augmentations. You're providing variability that hopefully will happen in the test set to improve your learning. And so this is actually a key crucial method for things like semi-supervised and self-supervised learning. So how do you leverage unlabeled data? Because you can augment the data even if it's unlabeled. You don't know they're labeled, but you could still apply these transformations to it. And so there's methods called, for example, rand augment, where you have a large list of 100 different transformations that we know in computer vision won't destroy semantic meaning of the data. So this can range from, just again, cropping, flipping, angle, rotation, things like that. And so there's also more sophisticated methods that even use reinforcement learning to choose which one to apply, for example. What we want to do is actually get away from kind of this domain knowledge that tells us, for each modality of data, what is a good domain augmentation or data augmentation. And so we want to develop kind of more general ones that don't do this in image space. They do it in feature space, not on the pixels themselves, but actually on the features that we extract using deep learning. And then also we want to do it in a learnable way. So we don't want to prescribe what augmentations to do. And so the setting that we'll look at is what's called semi-supervised learning, which you have a small amount of labeled data and a larger amount of unlabeled data. So for agriculture, this would be, you have a new region that you want to collect data from, and you're going to label it, but you have all these, collections of unlabeled data across the world. And so what we want to do is leverage that unlabeled data to do better on this small amount of labeled data in this new region. Again, some of the previous kind of state-of-the-art methods, such as mix match, have really used this data augmentation method. So specifically what they do is they take an image and, for example, an image of a cat, and then apply augmentation, so flip it. And then what they do is they enforce a loss that makes sure that the probability distributions output by the neural network for these two images, which has the same thing in it, are consistent, meaning that they're close together in the distribution. And so, I've seen some other talks here in this workshop talk about consistency losses as well. There's other methods that, for example, mix up, which actually interpolates between two different images. So it's not the same image, it's two different images. You do some linear interpolation between the images themselves, which is kind of weird. And then you interpolate between the labels as well to provide the actual ground truth kind of pseudo label to train with. And so again, we're using this to enforce what's called a consistency loss. And the limits of these methods is that they work in image space, right? So pixel space. So you kind of tell it, what are the augmentations that work in this image space that don't destroy semantic meaning. What we want to do is, in our method, do this in the more kind of complex way, so in a learnable way, such that it determines by itself what kind of augmentations to produce in feature space. So we've developed a method that's under submission called feat match, and the way it works is that it uses a graph convolutional neural network. So here, each image is a node in the graph, and then the edges between them define some kind of similarity measure, for example, cosine distance in the feature space. And so what we do essentially is, given image, a query image, we build a graph between that query image and all the other images. And then what the output of this graph convolutional neural network is refined features. So the input is the features from both the query image as well as the images from its neighborhood. And then it kind of combines in some weighted way to output a linear combination of the features to get refined features. And these refined features reflect not just the image appearance for that image, but also reflects kind of the appearance or the features of the neighborhood. So the features of similar things to it. And so you could view this as like a feature transformation. The input is, again, the features of all the nodes, and the output is some combined features. And so you can also view it in a data augmentation way, which is what we do, because we enforce the consistency loss. So you can see in this kind of down here, we take the features before the graph and the features output by the graph, and enforce that the predictions from those features should be consistent. So again, the same kind of consistency idea. So this is kind of viewing the graph transformation as a data augmentation itself, which has several advantages. It's in feature space, it's not in pixel space, and it's learnable. So you learn the parameters of this graph convolutional neural network to understand what kind of augmentation to provide, to produce. So here's kind of the kind of upshot is that, this is kind of computational expensive to produce a graph across all the images in your data set. There's like hundreds of thousands of images, let's say. So actually what we do is we extract a set of two prototypes. So given each class, we perform k-means on it every epoch. And so we extract the prototypes, and then we build a graph between the query image and those prototypes. And so to do this efficiently, we actually have a rolling computation of these prototypes. So what we do is we take the features that are already computed across the iterations of the optimization, and we then at the end of each epoch just take all those features, even though some of them may be stale, and perform k-means, and then we build the graph or continue learning this graph parameters. This is all trained end to end, and the only reason we do this is for kind of computational efficiency. So this is showing again that we kind of iteratively update these prototypes, but then we also learn all the parameters of the neural network. So to kind of differentiate our data augmentation method here, rather than doing augmentation in pixel space, we're one of the few that do in feature space, and we're kind of the only one that does both feature space and in a learnable kind of way. And so what we showed on pretty large data sets like Sci400 and mini ImageNet is that our method can get significantly better results in classification with a small amount of labeled data. So for mini ImageNet with 4,000 labeled examples, there's 100 categories here, so it's really 40 examples per category, which is a small amount. And you don't see that much of a degradation. So this is actually error rates. If you have 10,000 labels, you get a 5% or about 5% better. But it doesn't degrade significantly as much as some of these other methods as well, which degrades, for example, 10%. So we can be pretty robust to the amount of labeled data as we push the amount of data we have or amount of labels we have down further and further. One of the interesting kind of things that we're looking at is, what if your unlabeled data is out of distribution? So in the agricultural domain, this may be, again, if you're collecting in one region, but all your unlabeled data, you're just taking all the unlabeled data from all these other regions of the world. You still want to harness that unlabeled data to improve your performance using these consistency data augmentation ideas. And so what we showed is feat match. Our method actually performs much better, again, significantly better than the current state of the art in leveraging out of distribution labeled data. The way we test this is using a data set called DomainNet, where you have images of objects, but you also have like sketches or icons and things like that of the same object. So we can test, what if your unlabeled data is out of distribution, meaning that it's a different modality of inputs. And so again, our method is pretty robust to this out of distribution. It still can improve the performance as we get more and more out of distribution kind of data. So again, I think this is extremely relevant to the agricultural domain, because in many cases, there's a limited amount of unlabeled data in terms of the variety of unlabeled data you can gather within your particular region, but you can always just grab all the unlabeled data that exists across the world, which is kind of cool. And we're continuing to push the envelope on this setting, which is obviously much more challenging. So the second thing that I want to talk about is robust uncertainty-aware multimodal fusion. The motivation here is that often you have many different sensor modalities. So again, in agriculture, you may have multispectral, you might have hyperspectral, you might have depth estimation from structure from motion, and so on. And so what we want to do is be able to fuse all these sensor modalities together in a way that incorporates uncertainty. And the key thing is, you often have, for example, environmental degradations like snow, rain, and so on that differentially affect these sensors. So it might affect LiDAR in a different way than it affects imagery, for example. And so what we want to do is combine in an optimal kind of way all these different modalities, which is a hard problem. And so in this case, we're doing the application we're testing this for is self-driving cars. Actually in simulation with different degradations, but again, this is equally applicable for agricultural domain as well. So there's lots of current state of the art. So there's feature level fusion, input level fusion. So in the challenge, right, we have, I saw RGB and IR infrared. And so you can just put those channels together and feed it into the neural network. You can also, in our prior work, we've shown that actually you get a better bang for your buck in terms of accuracy and performance trade-off if you fuse the information at the middle layers rather than the input layers. And typically that actually rivals if you have much larger neural networks that process each modality and then combines it at the end. So it gets pretty good accuracy if you combine in the middle layers, but also it gets good performance in terms of reducing the computation time. There's also probabilistic level fusion that people have developed as well. So in our approach called UNO, which is uncertainty aware noisy OR, actually looks at this a little bit more interesting way. We're combining kind of three different ideas. One is we model uncertainty for each modality. So this is to deal with, for example, degradations that occur due to environment and other causes. And so we're modeling the uncertainty and we're weighting the different modalities based on this uncertainty information. We also have a spatial form of uncertainty estimation or quantification method that we'll talk about. And then we actually, after all this kind of machinery, all we do is we apply kind of Bayesian noisy or fusion method. What's cool is that we do uncertainty estimation per modality. So we weight the modalities and then we kind of normalize these weights across the modalities, and then we apply normal probabilistic fusion. And so this is a completely plug and play thing. So we can add or remove sensors dynamically, and we don't have to retrain anything in terms of the neural network. We just have per modality training, and then we kind of calibrate these things after the fact in a post-hoc way, which allows everything to be kind of plug and play, which is kind of cool. So in terms of the first idea, combining uncertainty measures, so there's a lot of ways to get uncertainty information from neural networks. They actually provide a probability distribution already, but we know that it's uncalibrated. It's very optimistic, even when it's wrong, if you give it like out of distribution data. And so there's lots of different methods, such as Monte Carlo dropout, entropy-based methods, and so on. What we find is actually each of these captures different types of uncertainty. So we want to combine them. The problem is, there's not really a direct way to combine them because they're all kind of unnormalized. So we developed kind of some method or technique to kind of calibrate, given a modality and a bunch of different uncertainty measures, how do you normalize these uncertainty measures in a way such that you can combine them effectively. And then the second idea is we add spatial temperature scaling. So temperature scaling is a method where you actually kind of soften the distribution depending on how you conditioned on the data. So if it's kind of out of distribution, then you kind of soften the probability distribution to make it higher entropy, more uncertain. And this already existed in other works, but we kind of applied a spatial variant of this because we found that actually this wasn't captured by all the other uncertainty measures we had. So this shows kind of the temperature network over here, where we actually have a neural network that estimates uncertainty by itself. And then it combines it with all these other three uncertainty measures here. We actually find we don't need some of the more heavy uncertainty measures like Monte Carlo methods, which are slow. So we actually, in our results, don't need that for good performance. And again, so what we do this is, we do this for each modality. We estimate these uncertainty measures, we combine them into one kind of weighting based on this uncertainty, and that is the output per modality. And then what we do is we combine these multiple modalities. Now that all the kind of uncertainty measures and the weightings have been calibrated using our methods, we then apply it using just a normal Bayesian probabilistic method. So we perform experiments here in AirSim, which is a simulator, photorealistic simulator to simulate things like fog, rain, and so on. And then we also, have done other data sets since then, but I'll show AirSim results. And what's cool is what we do is we train during relatively benign conditions. So we have things like here 0 fog or 50 fog, which is a small amount of fog. And then that's during training, so that's in distribution. But then we apply this to all sorts of out of distribution variations like frost, snow, blackout, and so on. And so we've never seen these kinds of degradations during test time, and we're combining modalities, in this case, RGB and depth. And so what we show is that our method is kind of significantly better than state-of-the-art, for example, SSMA, which is a state-of-the-art fusion method, complex fusion method. So we do, like 10 plus, or actually 18% better here on average over all these conditions, which is significant savings using our method. Here's some qualitative kind of results that show so on the left is the ground truth, on the bottom middle is the current state of the art, on the right bottom is our method. And you see that when degradations happen, the SSMA kind of has all these kind of incorrect predictions, whereas our method is actually really good across all these different types of degradation. So to conclude, there's been amazing gains in deep learning to perform processing of a large number of different types of sensor data, but really there's still a lot of limitations, especially for very in the wild kind of data like in agriculture, where you have a lot of variations across regions and so on, or the types of things you want to predict. And so what we showed is our methods can ameliorate a lot of these issues. For example, a small amount of labeled data, we have these kind of complex feature space augmentation methods that we can perform. And again, we've applied this to classification, but we can also do this for object detection. We've also shown uncertainty aware kind of data fusion methods where we have many different modalities, which is again very relevant to agricultural domain. But these problems are still not solved. We have significant work that we're doing in these kinds of domains as well. With that, I'd like to acknowledge all the PhD students without whom this work would not be possible, and then I'll be happy to